There's no doubt about it. 2025 has been a bit of a rough year for the Starship program. After 3 consecutive in-flight failures, hopes were high that the next attempt would see SpaceX finally solve the problems that have prevented the upgraded version 2 ship from making it past SECO. I think it's safe to say that the last thing any of us ever expected was for the next ship in line to fail a full 2 weeks before reaching second stage ignition. This was incredibly shocking to say the least. The only thing that could possibly be worse than the setbacks caused by the unexpected loss of a vehicle is suffering catastrophic damage to critical ground infrastructure in the process. If not for unprecedented levels of ambition and creativity, this could have easily caused a 4 to 6 month delay to the program while they rebuild everything that was destroyed. Thankfully, they were able to come up with a way to enable the ship to perform a static fire test on the orbital launch mount. Even though they managed to successfully avoid the worst-case scenario, this event really highlights how important this testing facility is to the Starship R&D program. While the reasons for that are fairly obvious, I realized that if there was ever a perfect time to document the evolution of the Massey's test site, it's probably now. So today we're going to explore how this remote stretch of land saved SpaceX from a major logistical nightmare and became one of the busiest rocket testing facilities on the planet in the process. My name is Zach Gold, and this is another CSI Starbase Deep Dive Investigation. What up, everybody? Welcome, and thanks for joining us. Before we get started, I just want to acknowledge the fact that I know this is not the topic that many of you are hoping I would be covering today, but hopefully you will forgive me because I think this is an important building block for future episodes. To be honest, many of the events we will discuss today are things I've covered in past episodes. In particular, this 2-part series I released in 2023. Normally, I try to avoid repeating information to the extent that I will today, but I think it's worth looking at them again in a different context. So instead of focusing on the importance of these events as it related to the first few test flights, we're going to look at the bigger picture and see how they influenced dramatic changes to the pre-flight testing procedure for Starship. I know this may not be the most exciting topic in the world, but I did my best to make it as entertaining as possible despite that. So with that PSA out of the way, let's get into it. After the high-altitude flight test of SN15, which ended with the successful landing back at the launch site, it was highly anticipated that SpaceX would use the next ship on the roster, SN16, to conduct a hypersonic flight test. Instead, SpaceX abruptly ended the suborbital flight testing campaign to pursue bigger plans. It was time to shift their focus towards orbital flight testing. Right off the bat, there were several logistical issues they needed to find solutions for. First, there was a long list of structural qualification tests that would need to be completed for the next generation of ship and 2 different versions of the booster. These qualification tests are performed on test articles designed to mimic specific components of the vehicle and typically require specialized test structures to apply loads that simulate conditions that will be experienced during flight. Because the test articles are often pressurized or filled with cryogenic liquids and are subjected to loads that have the potential to result in structural failure, the safest place to conduct these tests is at the launch site. Unfortunately, by mid-2021, there was only so much space available at the launch site given the massive construction operation for the orbital launch pad and tank farm. To make matters more complicated, they wanted to begin testing boosters as quickly as possible. Even though they were already in the process of constructing the orbital launch mount, it was still more than 7 months away from being semi-operational. So they needed a temporary solution in the meantime. Once the launch mount was ready, it would initially make sense to use it for performing cryogenic proof tests. Instead of creating a special test tank that could integrate with all 21 quick disconnect umbilicals on the OLM, they could use a real booster to help with function testing and commissioning various systems of the orbital tank farm. But these operations would eventually need to be performed elsewhere once launch operations began. If not, they would end up playing musical chairs on the launch mount. It would create quite the bottleneck if they had one booster waiting to perform cryo tests before engine installation, another one waiting to perform a static fire before final outfitting, while the third one is preparing for launch. Furthermore, there were structural tests for the booster that could simply not be conducted on the launch mount even if they wanted to. With these considerations in mind, they had already begun making plans to expand the site more than a year in advance. At the time, all they had were 2 suborbital test stands for ships. The proposed site plans released in 2020 called for 2 booster/structural test stands to be constructed near the existing stands. This would give them a dedicated location to perform cryo and thrust simulation testing, and potentially one of them could be used for structural qualification testing as well. And with a second launch pad, aka Pad B, there would never be a conflict between static fire testing and launch operations. But getting approval for this expansion would take some time, so they had to work around the existing infrastructure while simultaneously preparing for the future. Navigating around this situation required a lot of creativity, careful coordination, and just a touch of recklessness that I think is often underappreciated. When it comes to structural qualification testing, the push towards the first orbital flight test was easily the most intense period in the entire history of Starship development. In order to minimize the inherent risk that comes with launching the world's most powerful rocket, SpaceX needed to verify that the structural components of both vehicles would be able to withstand the forces experienced during the various stages of flight. For the ship, this included the nose cone, forward flap mounts, payload section, and header tanks, the thrust puck, aft dome, aft skirt, and the mounting hardware for the aft flaps. SpaceX was actually able to get a bit of a head start on some of these items before the final suborbital flight test. But with the booster, they were starting from a blank slate, so they would need to verify the design of the forward dome and forward sleeve, which is also referred to as the inner stage, the common dome, the 9 and 13 engine thrust pucks, and 2 different versions of the aft sleeve where the outer 20 engines are mounted. Between the 2 vehicles, I think the only major component that they may not have tested was the methane transfer tubes. I think it goes without saying, that's an extremely long list, and this is where that creativity I mentioned comes into play. If they were to create unique test structures for each component, then this process would take forever. So wherever it was possible, they went out of their way to create modular test stands that could be reconfigured to perform multiple different tests. In January of 2021, the development test engineering team began assembling their first multi-purpose test structure. While it's never been confirmed, I believe this was designed to eventually become one of the 2 booster/structural test stands mentioned in the 2020 document. The leg extensions that were originally delivered with this were clearly intended to provide extra stability. In my opinion, this would only be necessary if they were expecting to place a 70-meter tall booster on top of the test stand. The base structure was designed with 2 sets of attachments for additional hardware to be mounted, which would enable it to be quickly reconfigured for testing various components of the ship and booster. The first configuration is one we immediately began to refer to as the nose cone jail. After installing a cage structure on top of the base, it was used to perform structural qualification testing on SN12's nose cone, payload section, and forward flap mounting hardware to simulate the forces experienced during atmospheric reentry. The construction method for Ship 20's nose cone would be identical to the previous generation, so they were able to get this test out of the way before SN15's flight test. Shortly after completing this test, they removed the nose cone jail and installed a platform for mounting a 29-engine booster aft section. In the middle of the stand was an assembly of 9 hydraulic actuators used to test the thrust puck of the booster. This allowed them to verify the structural integrity of the thrust puck for Booster 3 using the BN2 test tank. Apparently, this gave them enough confidence to proceed to static fire testing without having to perform this test on the actual Booster 3. Once this was completed, they removed the platform and mounted it on top of suborbital test stand A so they could perform the first ever static fire test of a booster without having to wait for the orbital pad to be completed. This decision created another series of logistical issues. The 20 hold-down clamps for the structure, which were likely being fabricated at SpaceX's McGregor testing facility, had not yet arrived. So, because they were lacking a non-destructive clamping mechanism, the booster was welded to the structure. They had no plans of flying this, so for the booster tribe, it wasn't a huge deal because it was a good enough solution to allow them to perform the static fire test. This was perhaps a bit short-sighted, however, because once the test was complete, there was no way of quickly dismounting Booster 3 without using cutting torches and grinders. And if they cut it free, they wouldn't be able to place it back on the transport stand because the clamp interface at the bottom of the aft sleeve was essentially ruined. So instead of being able to scrap it back at the production site, it would need to be done at the launch complex. Unfortunately, there was only 2 mobile cranes on site that were large enough to perform this job, and both of them were tied up with construction work. During a brief pause between lifts at the orbital tank farm, the LR-11000 crane operator helped them remove the methane tank. But by the time that was finished, he was needed again at the orbital tank farm, which was already several weeks behind schedule. Because of this, the remains of Booster 3 would sit here for nearly 6 months until SpaceX finally bought their own crane and removed it themselves. If I had to guess, this is when the idea first occurred to the test structure design team that they should strive to eliminate the need for using cranes wherever possible. This would become a key design consideration on all future test structures that weren't already in development. Anyway, with Booster 3 trapped on the suborbital pad, the ring stand that the structures team was expecting to get back was trapped with it. And this was a problem, because with Booster 4 nearing completion, they kind of needed that ring stand. After waiting 4 weeks for replacement components to arrive from McGregor, crews busted their asses to get the new platform assembled as quickly as possible. In less than 2 weeks it was finished, this time with 20 hold-down clamps installed as well. But by then, it was already too late because SpaceX's second biggest mistake of 2021 was already in motion. Instead of waiting for the test stand to be completed, when Booster 4 rolled out for the first time to the launch complex, all 29 engines had already been installed. This meant they would not be performing thrust simulation testing on the 9-engine thrust puck. The decision to skip this test would come back to haunt SpaceX in ways they had not anticipated.
Well, actually, to be fair, it's probably more accurate to say that this would come back to haunt Elon. As much as I hate to say it, you could argue that everything that happened after this point was technically his fault.
As the new launch ring was being prepared for installation, E was pushing insanely hard to get a fully stacked Starship on the pad in less than 8 days.
I told the crane operators, what would you do if there's an asteroid heading to this planet in 8 days?
Yeah, exactly.
That's what they were told today.
If we operate with extreme urgency, then we have a chance of making life multiplanetary. Still just a chance, not for sure.
While this was a bold demonstration of ambition, rushing to put a checkmark next to this particular milestone did little to accelerate progress towards Starship's inaugural launch. This was ultimately part of a massive photo op, which would have been slightly less impressive without engines installed on the booster. And after the incredible effort that went into getting all 29 engines installed in less than 24 hours, they weren't about to remove them again. As a result, Booster 4 would become the only booster to go through its cryo testing phase with engines mounted. This would have been less of an issue if not for the fact that Booster 4 was also helping to function test and commission all of the new systems in the orbital launch mount and tank farm. And because a majority of these systems had not been tested beforehand, Booster 4 was basically used as a gigantic trash can for cleaning out the tank farm. Had the engines been removed prior to testing, they might have been able to clean out the propellant tanks, filters, and all of the internal plumbing. Instead, all 29 engines were contaminated with foreign objects and debris and rendered unsafe to operate. In my opinion, had they followed the same procedure they were already using for preliminary ship testing, all of this would have been avoided.
While it is extremely funny to blame Elon for this disaster, I think there is another important factor that influenced the situation and led to things going down the way they did.
I'm willing to bet a majority of people watching this episode have never even seen this multi-purpose test stand before, at least not in this configuration. That's because after all the effort that went into getting it ready for booster testing, it was never used for that purpose. And the fact that it was never used is another reason I'm convinced that it was intended to be one of the booster and structural test stands mentioned in the 2020 document. The structures team did their part in making sure this would be available by the time it was needed at the suborbital test site. Unfortunately, when it came time to act on this plan, SpaceX had not gotten past the regulatory hurdles that were preventing them from expanding the site to accommodate the additional test stands. More importantly, they were now staring down the possibility of failing to get approval to conduct Starship launches from Starbase at all. So the idea of expanding the site was likely off the table altogether. It's true that one of the proposed locations for this test stand was actually within the existing footprint of the site. But the fact that it would need to tie into the propellant distribution system of the suborbital tank farm presented a significant problem. The existing tank farm barely had enough capacity to perform a full cryo test of a ship, which meant there was nowhere near enough to do so for a booster. Without the ability to increase the footprint of the suborbital tank farm to add additional storage tanks, it would have been pointless to install the test stand here.
Sitting around waiting for permission to expand the site had the potential to delay the program by several months, if not years, and that was simply not an option. These test stands were absolutely critical to their plans, and without them, SpaceX was in desperate need of an alternate solution.
As development of the orbital pad continued to progress, they realized that the only other option for performing structural testing of a booster with a full cryo load was to use the orbital tank farm instead. So, in July of 2021, they began constructing 2 large pads near the integration tower, one for a ship and another for a booster. As the cryogenic feed pipes were being run between the tank farm and the launch pad, they installed additional fittings that would allow them to tap into these lines and divert the flow over to the auxiliary test stations. After constructing the giant berm to protect the tank farm from the exhaust plume of the booster, They installed propellant distribution lines on the backside of the berm for the 2 test stations. The lines that branched off the integration tower supply would be used for ship testing, while the ones for the launch mount were used for the booster station.
Had they waited an additional 4 months before installing engines on Booster 4, they could have used this station for performing the thrust simulation test. But ain't nobody got time for that, apparently. By that point, there were other important structural qualification tests that they were in a rush to complete and could not afford to skip.
As soon as the cryo stations were operational, a new multi-purpose test structure known as the Can Crusher was rolled out to the launch site. This impressive structure had the ability to be used for testing the thrust puck of the booster, but at the time, it was configured with 6 hydraulic actuators in the center for testing the new thrust puck and aft dome of the ship. The B-2.1 hybrid tank was one of the more interesting test articles SpaceX has ever created. Similar to BN2, it had a booster forward dome, but this time they included the inner stage as well, since that extremely important component had not been tested yet. We call this a hybrid tank because for the aft dome, they used the new 6-engine ship dome with the upgraded thrust puck design. The thrust puck had already been tested separately on SN15 when it was first introduced, but it was important to test it together with the new aft dome. Instead of sleeving the dome with a ship aft skirt, they used a booster aft sleeve instead. This allowed it to interface with the hold-down clamps and also enabled the test article to be used for stress testing the aft sleeve of the booster. After performing the first structural test, where the hydraulic actuators were used to apply loads to the ship engine mounts, the Can Crusher was moved back to the Sanchez site. They needed a bit more time to make modifications to the booster aft sleeve, which would take several weeks. In the meantime, they knocked out another important structural test. The GSE-4 test article was a shortened version of the vertical storage tanks at the tank farm. After installing some pressure transducers on top of the tank, they filled it with liquid nitrogen and let it slowly build up pressure until it finally popped. When using homemade tanks to store massive quantities of liquid propellants, it's a good idea to identify a maximum operating pressure. In this case, that max pressure might be defined as 80% of the final pressure observed before it ruptured. This event was a perfect example of why SpaceX needed a dedicated location to perform destructive testing. And this actually has nothing to do with the questionable decision to intentionally pop the tank with Booster 4 sitting less than 50 meters away, or the fact that there was a ton of construction equipment laying inside of the guaranteed splash zone. Let's be real, this wasn't the first time United Rentals would have 4K video footage to submit with their insurance claim, and it wouldn't be the last. No, the real issue here is that this test was ridiculously late. After installing the first 2 vertical storage tanks at the orbital tank farm 9 months before this test, SpaceX came to a surprising realization. With no internal or external stringers anywhere other than at the base, these tanks were not properly supported. As a result, they had to stop what they were doing and add reinforcements onto the 2 tanks they had already installed and the remaining 5 that were in various stages of completion. This caused a significant workflow disruption and was the first of many serious delays they encountered leading up to the first flight test. While the consequences of this were fairly minor in comparison to other issues they had with the tank farm, it's a good example of a situation that was completely avoidable. Had they performed a structural verification test on a full-scale version of the GSE tanks before SN15's flight test, they would have known there was a problem. In the end, they didn't perform the test that would verify the structural integrity of the reinforcements until 3 months after the final tank and outer shell had been installed, which is pretty wild. Speaking of avoidable situations, by mid-December, welders had finished adding a large hoop stiffener around the base of the B-2.1 test tank. This was kind of odd because there was no way they could have added identical reinforcements onto Booster 4, so you could argue they were attempting to cheat on the test. But as it turns out, this didn't really make any difference. After placing the cap on top of the test tank and subjecting it to compressive forces that would simulate flight-like conditions, their worst fears were confirmed when the aft sleeve buckled. It was at this moment when they realized that Booster 4's aft section was lacking the proper amount of structural reinforcement and would probably collapse before or during max Q. So even without the catastrophic contamination of its 29 engines, this would have likely been game over for Booster 4 and Booster 5 as well. I guess this means Elon was officially off the hook.
Now, any of these situations we just discussed would have been bad enough on their own. But dealing with 3 major issues related to structural qualification testing within the span of 6 months was a huge wake-up call for SpaceX. As an outsider looking in, it's hard to pinpoint a single reason why these situations were allowed to get as bad as they did in the first place. Some of it could have been a result of relying too heavily on CAD software and finite element analysis simulations, or somehow not realizing that certain structural components needed to be tested until it was too late. Honestly, I'm thoroughly convinced that the engineering team at SpaceX is far too talented for that to be the main cause, so I'm going to explain it another way. At the end of the day, these problems are all just side effects of the rapid iteration process. This is part of the reason why it takes so long for traditional rocket companies to get anything done. Overall, I think rapid iterative development has some major benefits, but one of the downsides is that it's pretty easy to fall into a pattern of systemic deprioritization of structural qualification testing. And yeah, I just totally made that up, but I think it's an accurate description of the problem, so what does it actually mean?
Well, let's start from the top. The main focus for the vehicle design team is obviously to design the vehicle. Now, let's say you have a second team who's responsible for designing test tanks to be used for structural verification testing. In reality, this job probably falls under the vehicle design team as well, but let's just go with it for the sake of this explanation. As I'm sure you can imagine, it's difficult to design a test article that represents the structural properties of the vehicle you're trying to verify before that vehicle is finished being designed. So the test article design team is always going to be a step behind. Next, you have the structures team, who actually develops the various test structures used to apply simulated flight loads on the test articles. They are at an even greater disadvantage because they have to wait for the vehicle and test article design teams. They may be able to complete a large portion of the test structure design in advance, but they are almost always going to have some dependency on the test article design team. Then you have the manufacturing team, who probably receives production drawings from the vehicle design team days or weeks in advance of the drawings they get from the test article team. So they can either put a hold on the work they've already started and move test article production to the front of the line, or they can handle jobs in the order they're received. This is of course assuming the vehicle isn't already fully stacked by the time they start producing test articles, which was the case more often than not. And finally, you have the actual structural qualification testing team. This team has to wait on everyone else I just mentioned. By the time they receive everything they need, the test article, test structures, and a place to perform it, testing of the vehicle may already be underway. Not only do they have to work around those schedules, but they also have to work around the schedule of multiple different construction operations happening at the launch site, which are likely being prioritized above everything else. This can quickly get out of hand, and in the worst case scenario, when the qualification testing is finally performed, you end up having to scrap multiple vehicles because of an inherent design flaw that wasn't caught until it's too late.
The opposite of this situation is making structural qualification testing the highest priority and not allowing vehicle manufacturing to begin until those tests are complete. But this has its own downsides because you can end up in a repetitive cycle of testing, finding flaws, redesigning, and testing again, and all of a sudden 5 to 10 years have passed before you actually get anything off the ground. Both of those outcomes were undesirable for SpaceX, so they needed to find a balance. While it's important to understand the full scope of this problem, today, we're just going to focus on the logistical issues with the actual testing process. It was painfully clear that there was simply way too much activity taking place at the launch site, and some activities, like structural qualification testing, could no longer afford to experience continuous delays. But despite how bad it looked from the outside, they were well aware of this, and little did we know at the time, they were already 6 months deep into coming up with a solution for the problem. In June of 2021, SpaceX began the process of acquiring the Massey's gun shop and shooting range.
Established sometime in the early 2000s, Massey's gun shop was known for its outdoor facilities, including a 300-yard high-power rifle range, a 50-yard pistol range, and a shotgun clay shooting range. They had a large selection of gun rentals available, including various machine guns and 50 caliber sniper rifles. Anyone who ever had the chance to visit this place can tell you that it was pretty awesome. It was also a great place for many SpaceX employees to come blow off some steam in their downtime.
When news of this deal first became public, it was widely assumed that this site would become a Raptor repair and testing facility. But as it turned out, they had much bigger plans.
While waiting for the sale to go through, SpaceX began using half of the property as one of their many storage yards. It would take some time for them to plan out the development of this site, which worked out well for the gun shop owners, who also needed time to build out their new facility in Brownsville. So, in the meantime, a berm was constructed to split the storage area from the shooting range to allow both operations to safely coexist. In May of 2022, the rifle range was temporarily shut down to allow contractors to begin grading the area that would eventually be used during the first phase of development. Once the groundwork was complete, this area was turned back over to Massey's so they could continue using it while SpaceX did the same thing with the pistol range at the front corner of the property. Over the next few months, they continued to open and close different parts of the range to allow groundwork to be completed. By the end of September, SpaceX was finally ready to fully take over the site, and the gun shop had officially moved out. After installing 2 horizontal liquid nitrogen storage tanks and a single cryo pump, they were able to finally begin transitioning structural qualification testing operations to this new facility. I'm sure the teams responsible for this testing were extremely grateful to finally have a dedicated location to perform destructive testing. At the time, there was a test article that had been sitting around at the launch site for 4 months waiting for an opportunity that would never come. As was the case with several test articles the previous year, there was far too many high-priority construction and testing activities taking place.
So when it was relocated to Massey's, it was a much welcome change of scenery. They no longer had to worry about interfering with construction activities at the launch complex.
To celebrate the occasion, they filled up the E-Dome test tank and popped the top like a bottle of champagne, sending liquid nitrogen flying 200 feet into the air. In December, they finally moved the can crusher to the Massey's outpost, officially putting an end to all structural qualification testing at the launch site. This was a crucial step towards improving the flow of operations. It was now time to shift their focus to the next area of ground testing that was in need of a major upgrade. For new Starships fresh off the assembly line, flight readiness testing is an important process that involves a series of different ground tests designed to verify that all systems of the vehicle will perform as expected during flight. These include ambient pressure tests, reaction control system testing, standard cryogenic proof tests with thrust simulators, igniter tests, pre-burner tests, spin prime tests, and multiple static fires using both the main and header tanks. The goal over time has been to eliminate some of these tests wherever possible, or reserve them for specific situations. As an example, pre-burner tests used to be a standard pop quiz for the ship leading up to the static fire test and would often require a full 8-hour closure window to perform. Eventually, these pre-burner tests were replaced with spin prime tests, which were sufficient enough to verify that the spin start systems were working properly without creating a huge fireball. These days, spin primes are only performed if an engine is swapped out after a static fire, which allows them to avoid having to do another static fire just to confirm the new engine is working properly. This is a significant improvement in the efficiency of the pre-flight testing procedure, which not only reduces the overall consumption of cryogenic commodities, but also reduces the total number of tests required. Perhaps more importantly, was the amount of time required to transition between certain tests. For example, with Ship 20, after performing its initial cryogenic proof test, they had to reconfigure the test stand for the thrust simulator test. As I mentioned before, this is extremely important for verifying the structural integrity of the thrust puck prior to engine installation and static fire testing. Now, in a perfect world, this transition would have been fairly quick. Initial cryo testing could be performed on test stand B, then the ship would be dismounted and rolled over to test stand A, where the thrust simulators were ready and waiting. And ideally, test stand A would always be in this configuration and would be the permanent structural test stand for ships. But with Booster 3 being stranded here for so long, they weren't able to introduce that type of workflow for quite some time. Instead, they had to take the more difficult approach of lifting the thrust ram assembly for the 3 center engines using chain hoists, attaching it to engine mounts, and then installing the legs one at a time. Once the center engines are taken care of, the process is repeated for the RVACs. After this series of structural tests were completed, the thrust ram simulator would be removed so they can install engines at the pad. Eventually, once SpaceX had their own crane, they would dismount the ship and send it back to the high bay for this operation instead. As you can tell, this whole process was a bit of a pain, but they were working on a solution to improve this for the future. In January of 2022, the GSE and structures teams ended up with some spare time on their hands while waiting for Booster 3 to be removed from test stand A. They had been preparing to convert the test stand from the old-style QD system on the bottom of the ship into the new style, which was already integrated onto test stand B. So, with an unused QD assembly on hand, they decided to test out the concept of allowing ships to perform their initial cryo tests without ever leaving the transport stand. After 143 days of sitting on test stand B, Ship 20 was placed onto the modified transport stand and then rolled over to the cryo testing station. Now, it's possible that this was just their way of function testing the QD before installing it in its permanent location. That way, if they found any issues, they could address it now instead of when it was actually needed. But I think it's more likely that this was intended to be a conceptual prototype that helped them decide how they wanted to design mobile test stands in the future. It's actually pretty convenient, if not for the extra work required to connect and disconnect all of these hoses from the pipes on the ground every time it's moved. So, While it was a clever idea, it was also kind of annoying. In May of 2022, they constructed a fixed QD structure that would allow the hoses to remain attached to the ground lines. Now all they had to do was roll the ship up to it, extend the QD plate, and voila. By the time Ship 24 rolled out for the first time, Booster 3 had finally been removed and the Test Stand B upgrade was completed. This created a perfect opportunity for them to see how quickly they could transition between operations. Within 24 hours, she went from the high bay to being plugged into the cryo stations, pressurized for testing, and then right before it was about to perform its cryo test, I'm not going to go into what happened here, but I have a super old episode you can watch if you weren't around for this particular event. After 7 days of repairs, it performed its initial cryo test and then moved over to Test Stand A, where the thrust simulator was already installed. This significantly reduced the amount of setup work required after placing the ship on the stand, and they were able to knock out the test 4 days later. At the time, this was extremely impressive, because if not for the header tank pressurization line incident, the full cryo testing procedure would have been conducted in less than 5 days.
This was another big step towards improving the flow of operations, which would become more necessary in the future once they reach the point where they're cranking out dozens of ships every year. Of course, they could have just skipped the cryo test station altogether and performed the same test on Test Stand A without using the thrust simulator. But a lot of time and resources could be saved by eliminating the need for cranes to be involved in this situation. So I think this was an important proof of concept for things to come once they moved these operations away from the launch site.
Returning to Massey's, a potential limiting factor to expanding the site as quickly as possible was the ability for SpaceX to acquire massive horizontal storage tanks. These are commonly referred to as hot dog tanks for obvious reasons. There is quite a long lead time on these tanks if they're purchased brand new. For a prime example of this, we can look at SpaceX's biggest mistake of 2021. This is when they found out that they wouldn't be able to use their homemade vertical GSE tanks for storing liquid methane. After this revelation, the sourcing team needed to find pre-certified storage tanks to replace them as quickly as possible. But acquiring this type of equipment on short notice doesn't really work out that well unless you happen to get lucky and find someone with unused tanks sitting around. That was the case for the first 2 tanks to arrive, but it would end up taking another 5 months for the rest to show up. I would say this caused a massive delay for the first orbital flight test, but thanks to the issues with Booster 4 and Ship 20, it probably didn't make much of a difference. When it came to sourcing equipment for Massey's, they didn't really have this problem thanks to the fact that they had more than a full year to prepare. And depending on how you look at it, they actually managed to catch a lucky break along the way and were able to source them from within. Shortly after completing their first integration tower at Starbase, SpaceX began constructing a second Starship launch pad at the LC-39 launch complex in Florida. At the time, they were worried that they would be forced to complete a full environmental impact statement for Starship operations at Starbase. This would have delayed the program by several years or prevented them from launching from Starbase altogether. The Starship launch pad at the Kennedy Space Center was basically an emergency backup plan in case that were to happen. But near the end of 2022, news broke that they would not be able to launch from 39A until they reached a point in the program where Starship was no longer in the experimental prototyping phase. Along with that, they would need to ensure that if something were to happen to the adjacent Falcon 9 launch pad, NASA wouldn't lose the ability to send crew and cargo back and forth to the International Space Station. So SpaceX immediately got to work designing and constructing a brand new crew access tower for the Falcon 9 launch pad at Slick 40. But that would take some time, and it didn't change the fact that Starship was nowhere close to being out of the experimental phase. Given the major setback to their plans of launching Starship from 39A, there was now a huge amount of GSE equipment that would end up sitting around collecting dust for more than 3.5 years. This included 4 horizontal water tanks and a large collection of high-pressure gas cylinders, 14 hot dog tanks, 2 vertical methane storage tanks, and at least 8 subcoolers and cryogenic transfer pumps. You might say this was the ultimate garage sale opportunity where everything is free as long as you can handle shipping. So in late October, SpaceX removed 3 hot dog tanks and transferred them to Starbase using an ocean barge. After arriving a month later, they began installing the 3 tanks, which would end up becoming the first liquid oxygen storage tanks. The next week, they got to work constructing the foundation for the ship cryo testing station, which was nearly identical to the one at the launch complex near the integration tower. The only difference was this time they reinforced the pad with 54 continuous flight auger piles drilled 80 feet deep into the ground. The geology at Massey's is a bit different than the launch complex, but I think this was a reaction to their experience with the vertical tank farm, which had been slowly sinking over the past 12 months. Learning an important lesson from that situation, SpaceX made it their mission to never allow this to happen again. From this point on, any structure that would support more than 50 tons would be constructed with a heavily reinforced foundation. While forming the 5-foot thick pad, they added a ring of embed plates to support the test stand before filling it with concrete. After extending the distribution lines from the LOX and nitrogen farms over to the new testing station, they installed a fixed QD structure identical to the one developed for the launch complex. Ship 25 rolled out to Massey's for the first time on February 23rd to help with commissioning the new cryo station. These initial tests would be conducted while the ship was on its transport stand, but it would take another 2 months to get the GSC systems ready before they were able to do that. This is pure speculation, but it seems like someone on the operations team may have requested an additional LOX pump to be added before the first test. Doing so would cut the propellant loading time in half, bringing it from 4 hours down to 2. But the more pumps you use, the more gas you need to backfill the tanks as they're being drained at a higher rate. So they also had to finish expanding their gas generation system, which was now supporting 2 tank farms instead of 1. In the meantime, the structures team began assembling the base of the new mobile test stand that would be used for cryo and thrust simulation testing. After welding the outer ring section together, additional steel frame supports were added to the middle of the structure in a pattern that resembles the radiation hazard symbol. The hydraulic actuators for the 3 center engines and raised access platforms are mounted to a circle in the center. The actuators for the RVAC engines are mounted on top of the 3 evenly spaced arcs. On either side of those actuators are cylindrical columns which are used to support the upper ring wall around the access platform. The 6 hold-down clamps are mounted to the outer ring, making this a super low-profile structure. Once the ship is lowered on top, the only way to get inside of the aft section is by climbing up through the gaps between the 3 arcs. Eventually, they installed stairs and ladders in these locations, along with walkways that go all along the outer ring. There is also a set of stairs to reach the raised platform, so workers can easily access the top of the actuators. After the ship is secured by the clamps, the actuators are extended up to the aft dome and then bolted onto the engine mounts. On the upper ring wall, there are another 6 hydraulic actuators mounted horizontally, with 2 attached to each of the gimbal mounts. For reference, these are what the gimbal mounts look like. They pivot on 2 different axes in order to achieve a full range of motion. From this perspective, the upper component gimbals side to side, while the lower one gimbals front to back. From what I can tell, there is one actuator mounted to a bracket extending from the lower pivot, while the second actuator is attached to the upper one. This allows them to simulate loads that will be experienced while the engines are gimbaled outwards at extreme angles during the aggressive flip maneuver before landing. This is something they did not have the ability to do with the original thrust simulator system. In total, there are 18 hydraulic actuators after you include the 6 small ones used for the hold-down clamps. To minimize the amount of setup work required before testing, the entire hydraulic control system, including the reservoir, pump, and several accumulators, are all mounted on board.
Overall, this new test stand was a significant improvement that managed to alleviate all of the pain points they had encountered during the 2 previous years with the suborbital test stands.
Anyway, with the upgrades to the GSC systems complete, Ship 25 was finally able to perform the first ever cryo test away from the launch site on May 5th of 2023. With ship cryo testing out of the way, it was time to address the same operation with the boosters. Pre-flight testing for boosters essentially consists of the same procedures they use for the ship. In other words, initial cryo testing should ideally be followed by a thrust simulation test to verify the structural integrity of the 13-engine thrust puck. Pre-burner tests would probably have been a bit too dangerous with this many engines, so instead they performed spin prime tests followed by a separate igniter test. If everything is functioning as expected, then they proceed to static fire testing. After retiring Booster 4, SpaceX had to completely retrofit the launch mount to support the next generation booster. Not only did it have 33 engines instead of 29, but it was also the first to use the new Raptor 2 engines. By the time Booster 7 made its debut, SpaceX was anxious to get it ready for static fire testing as quickly as possible. This time around, they decided not to skip any steps and follow the same testing procedure used for the ship. While waiting for the launch mount upgrades to be completed, they reconfigured the can crusher to support booster testing. Instead of the 6 hydraulic actuators in the middle, there were now 13. Following its initial cryo test on the launch mount, Booster 7 was carried over to the can crusher to perform another cryo test on top of the thrust simulator.
Similar to the ground testing procedure for ships, this would eventually become standard practice for boosters. Like I said, it's extremely important to catch any manufacturing defects before you begin engine testing.
This test seemed to go well until SpaceX proceeded to detank the booster, which is when it suffered its first testing-related injury as its methane transfer tube collapsed due to a pressure imbalance in the header tank. After repairs were completed, it performed multiple cryo tests, spin primes, and static fire tests on the launch mount until it was finally ready for flight. In between all this, they also conducted a series of tests on the B7.1 test tank on top of the can crusher. This was to verify that the upgraded reinforcements on the aft section would solve the issues they experienced on the previous design. These tests spanned over a period of 3 months due to an unexpected issue that required repairs on the tank and then another repeated test. After this, there were several other tests that were waiting in line to use the can crusher, which were all critical to the first flight test. This included the aft skirt of the ship, the inner stage of the booster, and then another test of the ship's aft skirt after the first had failed. Eventually, the can crusher was transferred to Massey's for even more testing of the ship's aft section, which required the use of liquid nitrogen. So, by the time Booster 9 rolled out for cryo testing in December of 2022, there was no way to perform the structural verification test of its thrust puck. Along with this, there was a massive amount of work that was taking place on the launch mount that they didn't want to interrupt. This included replacing the blast surface with high-strength Fondag, installing a ton of external shielding, and adding load cell sensors into the hold-down arms, which would need to be ready in time for calibration testing by the end of the year. Keep in mind that, even though it would be another 3 months until they were actually ready for Flight 1, SpaceX was perpetually operating as if it was a mere 2 weeks away. With that said, they wanted to knock out this cryo test as early as possible so they could begin installing engines on Booster 9. This is a fairly long process, and they were hoping for a quick turnaround time between flights. So, following in the footsteps of the Starship team, they decided to perform the cryo test without the booster ever leaving its transport stand. But a fully loaded booster is about 3 times heavier than a ship, and these version 1 transport stands weren't exactly designed to support upwards of 3,500 tons. So instead of doing a full cryo test on both tanks as they had with Booster 7, they performed a partial load of the liquid oxygen tank, which was immediately followed by another partial test of the fuel tank using liquid nitrogen. 8 days later, they performed a second test, this time only focusing on the methane tank. After completing this test, B9 went back to the Megabay for engine installation. In total, this process took about 14 days, but in the future, they had plans of bringing this down to 4 days or less. Despite the 7-month delay between IFT-1 and IFT-2, B9 would go on to be the only booster to ever fly without performing a structural verification test. You know, the crazy part about that situation is, anyone who was a part of the booster manufacturing team at that time knows that if any vehicle should have been checked for manufacturing defects on the thrust simulator, it was probably Booster 9. But that's all I'm going to say about that topic. The important thing is, this was a risk that they would prefer to never repeat again. A structural failure of a booster in flight carries a lot more risk than if the same thing were to happen with the ship. Returning to Massey's, in the aftermath of IFT-1, activities at Massey's began to pick up dramatically. Alongside a massive amount of work needed to expand the capabilities of the site, there were several extremely important qualification tests for verifying components of the ship and booster that would need to be completed. This is when the relocation of all the structural testing away from the launch site truly started to pay off. Within a 7-month period, SpaceX was able to perform structural verification tests on the new stretched panel design for the Starship nose cone, the new stretched panel E-dome that I mentioned earlier, 2 separate iterations of the aft section reinforcements on the ship, the hot stage ring, 2 destructive tests to failure, and after the failure of the flight termination system on Flight 1, they tested an upgraded version of the FTS system on one of the tanks they no longer had a use for. The best part is, all of this was completed without using a single minute of their yearly allotment of beach closure hours, or causing disruptions to the massive reconstructive surgery for the launch mount after the damage sustained during IFT-1. Alright, here we are. Good lord, this place is way bigger than the high bay. Can't believe it's still vacant after all this time. I can definitely get used to this view. Anyway, in the middle of all that structural qualification testing I just mentioned, SpaceX began expanding the tank farm at Massey's so they would have enough capacity to actually begin testing boosters. Back in January of 2023, the Pad 39A capital equipment sourcing team was robbed at gunpoint for a second time by the Starbase GSE squad. This time, the bandits made off with 3 large hot dog tanks, 4 water tanks, 2 sets of high-pressure gas cylinders, a bunch of large pipes they would need for the booster bidet system, and a booster transport stand. While the foundation for the new liquid nitrogen tanks was being prepared, they simultaneously began constructing the pad for the booster cryostation. Similar to its neighbor, the foundation was formed with 56 CFA piles to support the weight of a fully loaded vehicle. The pad is roughly 5 feet thick, with embedded steel plates for bolting the test structure to the ground. For the booster QD, they decided to upgrade from the janky setup they were using at the launch site Cryo station to one that could telescope outwards like the BQD on the launch mount. As this was being assembled, the base of the test station was being constructed nearby. Inside of the steel base structure are pedestals to support 13 hydraulic actuators. Since the purpose of the thrust simulation test is to verify the structural integrity of the thrust puck and the welds that join the aft dome to the inner wall of the tank, they only needed to apply loads to the 13 center engines. The outer 20 engines are mounted to a structural ring around the perimeter, which is arguably the most heavily reinforced part of the vehicle. Once the base structure was done being assembled, it was filled with cement to increase stability and keep the center of mass as close to the ground as possible. After this, the ring structure for mounting the 20 hold-down clamps was added, and more than likely filled with cement as well before closing each of the gaps. Welded to the embedded steel pedestals in the center of the base are 13 clevis brackets for mounting the hydraulic actuators, which are surrounded by an access platform. On the outside of the structure, they added 4 sets of extensions, or outriggers, which I can only assume were filled with cement like everything else. These outriggers allow the base structure to rest on top of pedestals, which are welded to the embedded steel plates inside of the foundation of the pad. Similar to the ship cryo stand, all of the hydraulic systems are mounted on board to allow this to be a fully self-contained mechanical system and reduce setup time. One big difference is that there doesn't seem to be any mechanism to allow them to simulate loads experienced while the engines are gimbaled outwards. I guess they decided that wasn't necessary for booster testing. While this new test stand was being constructed, Booster 10, having nothing better to do at the time, decided to make its trip over to Massey's to help out with the commissioning of the new cryo station. Shout out to the road construction crews because it took nearly 2 years to completely rebuild the road between Sanchez and the Massey's outpost. In the process, they significantly increased its load-bearing capacity. Without this, transporting these super heavy boosters back and forth would have quickly caused catastrophic damage to Highway 4. The combined weight of the booster, transport stand, SPMTs, and 4 sets of counterweights used to prevent the vehicle from tipping over easily exceeds 500 tons. Similar to the situation with Booster 9, because Booster 10 would be tested on its transport stand, they wouldn't be able to perform a full cryo test. On top of that, the 3 new liquid nitrogen tanks were still being rigged into the rest of the system, so they didn't have enough capacity to fully load either of the booster's tanks anyways. The funny thing is, even after they were operational, it still wouldn't be enough to fill the massive LOX tank of the booster. I'm not sure if this was some kind of miscalculation, but they would end up having to rent 2 king-size trailers to make up the difference until they finally got their hands on a 7th hot dog tank 4 months later. The limited capacity wasn't an issue with Booster 10 because they were mainly focused on commissioning the new systems. So instead, they performed a partial test on both tanks. This is the only time they have ever tested both tanks at the same time since booster cryo testing was relocated to Massey's, which is a really odd mystery that I've spent a lot of time trying to figure out. But more on that later. While this was happening, the mobile test stand for the ship, now fully completed, was on its way to the production site to pick up Ship 28. After 2 long years, the test structure engineering team had finally reached the first major milestone of their plan for optimizing pre-flight testing. On July 28th, Ship 28 performed its first cryogenic proof test, followed by what I can only assume was the structural verification test using the thrust simulators 6 days later. Being able to perform these tests from a single stand without the need for a crane to be involved was a game changer. The next day, it returned to the build site for engine installation. A month later, the mobile thrust simulation stand for the booster finished assembly and was now ready for action as well. After it was moved to the production site, Booster 10 was lowered on top of it, and when it rolled out for the first time, we noticed a pretty interesting detail about it: no counterweights. This was a bit surprising because with a normal transport stand, whether the booster has engines installed or not, it requires 240 tons of counterweights on the SPMTs. This is for stability to bring the center of mass closer to the ground and reduce the likelihood of it tipping over. These transport stands are probably not as heavy as they look thanks to being constructed with tubular steel. For comparison, the ship used 200 tons of counterweights when it's transported without engines and 160 tons after they're installed. And with the new mobile thrust simulator stand, nothing really changed. Still 200 tons. So the fact that the booster can be transported on the cryo station with 0 counterweights is a sign of how insanely heavy this structure is. Anyway, after being transported to Massey's, B-10's testing campaign was a bit different than Ship 28. Instead of testing both tanks at the same time, they started off with the methane tank. A few days later, they completed a LOX cryo test, which lasted for about 3 hours before adding a small amount of fluid to the methane tank and continuing the test for an additional 2 hours. I can only assume that this second phase of testing is where the thrust simulation test occurs, and that it requires the methane transfer tube to be filled. This may have something to do with protecting the downcomer from being crushed, but I'm not really sure. I think analyzing what's happening during these tests is super interesting, but for the sake of not making this episode longer than necessary, I'll save that for another time. With structural verification testing and ship and booster cryo testing out of the way, the next major focus for improving the flow of pre-flight testing was static fire testing of the ship. In my opinion, this one was arguably the most important. Up to this point, I would say that each of the topics we have covered could be categorized as logistical issues. From a functionality standpoint, the original infrastructure for cryo and structural testing worked just fine. Change was driven by the fact that the process was slow, often got in the way of or were delayed by other operations, and the dependency on expensive heavy lift equipment that was better used elsewhere. The same logistical bottlenecks affected ship static fire testing as well, but they also had another problem that was arguably a bit more serious. This is mostly centered around the fact that the test stand, which was fine for cryo and thrust simulation testing, had a fundamental flaw that made it ridiculously ill-suited for static fire testing. To be honest, it's actually quite perplexing that this was ever allowed to happen. When we take a quick look at how engine testing is conducted at SpaceX's McGregor testing facility, we can see a very different approach from what happened at Starbase. During the early days of Falcon 9 testing, the first stage boosters were tested on top of a massive 220-foot tall tripod stand with a gigantic flame bucket at the bottom. After upgrading Falcon 9 to the full thrust variant, the tripod stand could no longer handle the increased thrust of the new booster. So a new test stand was built adjacent to the tripod, which featured a trench with a massive upgraded flame bucket at the bottom to divert the hot exhaust gases. Thanks to the deluge system and flame trench, Falcon 9 static fires became a lot quieter. In 2019, the tripod stand was repurposed as a vertical test stand to help support Raptor development. So for several years, they tested Raptors either horizontally or 220 feet in the air above a flame bucket. But for some reason, when it came time for the initial design review of the static fire test stand for Starship, it seems like some design constraints may have been prioritized above others. All right, everyone, what do you think? Ooh, wow. Amazing. Relatively simple design, which should be easy to fabricate and assemble in weeks instead of months. Perfect. We literally just finished modifying one of those aircraft catering trucks for easy install and maintenance of Raptors. Looks like it would fit between those legs no problem. Wait, don't you guys think it's a little bit too low to the ground? I feel like we need a flame cam. We mount little cameras on the legs, and then we have a clean view right into the skirt while the engines are firing. Genius. And you could literally prefab these, pack like 3 of them into the payload section, and have little robots assemble them on Mars. Oh, wow. Shit. Yup. Send it to fabrication. Let's get the ball rolling. I just don't get it. The second stage Starship has 180% more thrust than a Falcon 9 booster. Firing 6 of some of the most powerful liquid-fueled rocket engines ever created from just 8 meters above a flat surface was always a recipe for disaster. This is like an adult using a toddler's potty training toilet after eating 6 cheesy double beef burritos from Taco Bell. Sorry for that visualization, but I feel like it's an accurate comparison. Anyway, I think one could argue that the experiences they had on this pad should have been an indication that there was zero chance the orbital launch mount was ever going to work as originally designed. But let's not get into that. Instead, I'll just quickly summarize the list of lessons that SpaceX learned while performing static fires on this baby-sized test stand. To protect the blast surface of the pad, they installed a tiny water deluge system, if you can even call it that, which ended up being completely ineffective. When testing SN4, 5, and 6, it wasn't as noticeable that there was a problem with this test stand, which was probably due to the fact that these were single-engine tests. But when they moved on to SN8, it became a lot more obvious. In November of 2020, they performed a semi-long duration static fire test, which resulted in chunks of concrete flying all over the place. Unfortunately, there wasn't much that could be done about this, so they continued with testing. On the third attempt, the deflected material ended up causing severe damage to the vehicle. This included a stream of molten metal pouring out of the skirt, and damage to the pneumatic system, which controlled the ship's ability to vent its propellant tanks to relieve pressure. Thankfully, some of the built-in safety systems did their job and were able to prevent the complete destruction of SN8. After this close call, attempts were made to prevent it from occurring again. They added a layer of ceramic-filled epoxy known as Martite on top of the concrete. Given that this material is commonly used in aerospace applications to protect exposed structural steel from hot rocket exhaust, they hoped that this would solve the problem. It didn't. As it turned out, the heat and pressure generated by the Raptor engines was just far too great. Honestly, I didn't even know it was possible for concrete to glow red hot like this. Luckily, they were able to spread the burden between two static fire stands to reduce the damage. Eventually, they replaced the Martite with a high-strength refractory material known as Fondag, which they would later end up using under the orbital launch mount as well. As you can probably guess, this wasn't much better, and it still sent chunks of material flying hundreds of yards away. The resulting debris cloud became the TPS team's worst enemy as it repeatedly damaged tiles on the ship. All hopes of being able to monitor the tests from below were literally crushed, as every single camera mounted on the legs of the test stand were obliterated. Nothing could survive these conditions. Even worse was the fact that the 6 Raptor engines were being forced to compete in the World Series of Russian roulette against their will. This regularly resulted in technicians having to replace engines that were otherwise performing great during the test. In nearly every way imaginable, the suborbital test stands were a hot mess. It was clear that in order to achieve the goal of streamlining pre-flight testing, a massive overhaul of the ship's static fire stand was required. Little did we know at the time, but the plan to begin constructing a second orbital launch pad was already well underway, and SpaceX would begin shipping completed tower modules from the Florida facility to Texas immediately after Flight 2. But after failing to get approval to expand the footprint of the complex, the originally planned location for Pad B was no longer an option. Because of this, there was now only one place they could put it. So, at the end of 2023, the race was on to relocate ship static fire testing to make way for the new launch pad. They needed a flame trench, and they needed it fast. In November of 2023, SpaceX began the largest and most important phase of expansion at Massey's. I gotta tip my hat to the teams responsible for coordinating all of this work. From a project management perspective, the phased approach of Massey's development was pretty genius. By starting off with building the nitrogen farm, they enabled structural qualification testing to move to Massey's. When it came time to build out the cryo testing stations, 50% of the infrastructure required for the test stations was already in place. With the nitrogen farm operational, they could focus on adding liquid oxygen storage and distribution systems. Now, when it came time to build out the static fire test stand, once again, almost half of what they needed was already operational. They had LN2 and LOX farms. All that was left was the fuel farm, flame trench, and water deluge system. One capability they would need to add to the existing infrastructure that wasn't already present was the ability to densify liquid oxygen. As many of you know by now from watching the propellant loading process at the launch site, this is accomplished by passing liquid oxygen through coiled tubes submerged in liquid nitrogen. This wasn't necessary for cryo testing, but it is for static fires because the Raptor engines are finely tuned to expect subcooled propellants. Luckily, the Starship launch pad at KSC still had a collection of equipment that they wouldn't be needing anytime soon. With Christmas right around the corner, the GSE team put together another wish list and snatched up 2 LOX and CH4 heat exchangers and 2 multi-stage vertical pumps that they would need for the methane farm as well. The final item on the list was bulk storage tanks for methane. Unfortunately, they had already cannibalized all of the large hot dog tanks, so they had to settle for vertical storage tanks instead. The funny thing about these tanks is that they were previously expected to be used as LNG storage containers for the large backup generators at Starbase. As best I can tell, they were initially planning to transition from the small road tankers they were using to a large bulk storage system. This upgrade would have allowed them to provide continuous power to the adjacent air separation plant. It's always been a major goal for SpaceX to produce their own cryogenic commodities. But after a change of plans in early 2022, 2 of the tanks were shipped off and donated to Pad 39A to be used for some unknown purpose, only to be repossessed 20 months later and sent back to Starbase. As equipment began to trickle in, the demolition crew was given the green light to pull the trigger on Test Stand A. This left Test Stand B to handle the 5 remaining static fire tests on its own. Over the next few months, a massive amount of effort went into completing several simultaneous projects as quickly as possible. First, there was the methane farm, which squeezed bulk storage tanks, pumps, subcoolers, pressure building systems, high-pressure gas generation and storage, and methane recovery system into an extremely small footprint. The flame trench was constructed about 2 to 3 months faster than it would have otherwise by overlapping multiple processes that would normally be completed in sequential order. After waiting for a convenient gap between the ground testing campaigns of the Flight 5 and 6 vehicles, they integrated the liquid oxygen subcoolers into the existing LOX and LN2 distribution lines. From there, they extended the LN2, LOX, and nitrogen gas supply, along with many other high-pressure gas lines, to join up with the commodities being supplied by the methane farm. These were routed to a series of 5 distribution manifolds. These control loading and detanking of liquid oxygen and methane, the pre-pressurization system for both the ship's propellant tanks, and 4 sets of panels for loading high-pressure gases into the COPV tanks on the ship. All of these commodities are routed to a gantry above the trench where the ship QD is located. To protect these sensitive areas, they installed a pressurized water tank which feeds a fire suppression system above all the high-pressure gas distribution panels. This fire suppression system extends up to the gantry where there are nozzles in front of and behind the ship QD assembly. As the trench was nearing completion, they began constructing a clever, first-of-its-kind gas-driven water deluge system. While this was being installed, components for the flame bucket and its supporting framework were shipped from the McGregor testing facility where they were being fabricated and assembled on site. On that note, I'm fairly confident that every single system I just mentioned was designed by the GSE team at SpaceX's McGregor testing facility. Of course, there was no way to know this for sure, but with a trained eye, you can easily see their fingerprints all over this. So, to those of you who are wondering why it was designed this way with the methane farm so close to the test stand and all of the plumbing above ground, all you have to do is look at any of the static fire stands at McGregor, and the answer is pretty clear. If I had to guess, the only component of this entire system that may have actually been designed at Starbase would have been the mobile test stand. Keeping with the trend of eliminating the need for cranes wherever possible, the structures team designed the static fire test stand to be robust enough to support transportation of the ship. Compared to the 2 cryo stands, its design is incredibly simple. The large ring wall is constructed out of hollow steel box sections similar to the orbital launch mount. Once the sections were welded together, it was placed on top of 4 tall standoffs so the legs could be attached. There's no evidence of this, but I believe that after they finished welding them to the ring wall, the legs may have been filled with concrete before they were capped off. To allow this to be transported by SPMTs, there are horizontal beams on 2 sides of the stand attached between the legs. Similar to the suborbital test stand, there are 6 clamps to lock the ship in place. There are 6 additional blocks between each of the clamps to improve the weight distribution when the ship is fully loaded. When firing the RVAC engines at sea level, there are braces installed around the bottom of the extended nozzles. On the inner wall of the ring, there are 6 posts with clevis brackets mounted on top. On each of these posts, there are 2 struts that attach to the nozzle braces to prevent them from vibrating against the aft skirt of the ship. As you can see, there is very little clearance between the nozzles and the skirt. I mentioned earlier that the ability to service the engines and swap them out if necessary was an important design consideration for the stand. Thanks to the sliding platform on top of the trench, Raptor service trucks can easily drive underneath the ship in the event an engine needs to be replaced. As a fairly recent addition, a heavy-duty circular platform was constructed to eliminate the need for Raptor service trucks. Taking some inspiration from the maintenance platform for the orbital launch mount, they mounted motorized chain hoists to the outer wall of the ring stand to raise and lower the platform. On May 7th of 2024, the static fire stand was rolled to the production site for the first time. Waiting inside the ship bay was the infamous Silver Bullet, aka Ship 26. According to a poll that I posted on X last year, Ship 26 was overwhelmingly voted as the most beloved Starship ever produced, and it wasn't even close. Unfortunately, I was unable to find this post on my profile, so you're just going to have to take my word for it when I say that almost everyone was extremely disappointed that it was never given the chance to fly. Personally, I'm not that sentimental, but it's hard to get over the fact that we never learned what SpaceX's original plans were for that beautiful 9,000mm projectile. The good news is, before it was scrapped, it was given the honor of serving as a test article to commission the new static fire test stand. Less than 3 days after Ship 26 arrived to Massey's, the demolition crews began dismantling Test Stand B at the launch complex. This officially marked the end of an era. Before bringing down the last section, workers were asked if they had any final words that they wanted to say. At that point, one of the TPS technicians who had spent countless hours replacing tiles that were damaged during static fire tests climbed on top of the test stand and proceeded to beat the shit out of it with a sledgehammer. Sometimes actions are better than words. The demolition of Test Stand B is perhaps the ultimate sign that SpaceX never expected to experience a catastrophic failure on the new static fire test stand. The inaugural static fire test would not take place for another 24 days, so in my opinion, this was fairly risky. Thankfully, they would not end up regretting this decision. On June 3rd of 2024, Ship 26 performed the first ever static fire test at Massey's. For most fans who had grown used to the up-close and personal experience of watching these tests live with amazing views from the various LabPadre and NASASpaceflight cameras, this was kind of a sad day. But putting our feelings aside, this was a massive improvement for SpaceX. Thanks to the flame trench, the issue of tiles being damaged by debris during static fire tests has been completely eliminated. And as far as we can tell, the amount of engines swapped out after these tests has gone down dramatically. With the flames being channeled away from the test stand, it's allowed SpaceX to capture some pretty amazing views looking up into the skirt of the ship. It's enabled them to perform long-duration tests, which would have almost certainly dug a hole all the way to China had it been performed on the suborbital test stands. Not only is this awesome for us as fans, but I imagine it's also extremely helpful for the engineering teams monitoring these tests. And finally, by moving all ground testing other than booster static fires to Massey's, they have been able to reduce the amount of beach closures by more than 70%. With the goal of eventually launching 25 times a year out of Starbase, this is extremely important. Without Massey's, SpaceX would need to close the beach somewhere between 150 to 200 times every year. But by moving ground testing away from the launch site, that number drops down to somewhere around 50. And when they reach the point where they're comfortable reflying boosters without performing static fires, that number will decrease even further. So while this does complete the story of how SpaceX seamlessly transitioned pre-flight testing operations away from the launch site, the evolution of Massey's is still ongoing. Even with the core functions of the site fully operational, there was no time to relax. Just like every other area of Starbase over the past 6 years, Massey's has been undergoing continuous upgrades. Not only are they increasing the capabilities of each test station, but they're also in the process of transitioning relevant infrastructure to make it compatible with the next generation of Starship. For the sake of not making this episode 2 hours long, I'm just going to give a brief summary for now. In March of 2024, they began constructing a new multi-purpose test structure to replace the can crusher. This next-gen structural test stand would allow them to stress test components of the vehicle in ways that they did not have the ability to do previously. The booster cryo test station has been operational for nearly 2 years at this point, but we have yet to see them perform a full cryo test of a booster. After all this time, Booster 10 remains the only one to ever load both tanks at the same time. Every booster since that initial test, aka boosters 11, 12, 13, 14, 15, 16, and 17, have all performed partial tests where the methane tank is tested separately from the LOX tank. This made sense for boosters 11, 12, and 13 because it was obvious they didn't have enough liquid oxygen capacity on site to actually fill the LOX tank of a booster. So instead they used liquid nitrogen in both tanks, which meant they could only test one tank at a time. But in August of 2024, they added 4 massive hot dog tanks to the LOX farm, which should have allowed them to begin performing full cryo tests like they did on the launch mount. The fact that they still haven't done this is a mystery that I don't fully understand yet. Although I admit I did remove 15 minutes of speculation on that topic from this episode. After Booster 17's cryo test, which was the last of the V2 boosters, the structures team began preparing for the next-gen version 3 booster. This requires a new mobile thrust simulator test stand and a complete reconfiguration of the booster QD, which is now split into 2 separate umbilicals, one for fuel and the other for oxidizer. It's possible that a similar reconfiguration will be needed for the version 3 ship, which should feature orbital propellant transfer capabilities. For the static fire test stand, upgrades were made to the water deluge system to allow them to perform longer duration hot fire tests lasting up to 60 seconds. It was expected that after the final static fire test of a version 2 ship, SpaceX would begin upgrading the fuel farm to increase its capacity as well. The 2 vertical storage tanks were a quick solution that allowed them to get the static fire stand operational as quickly as possible. Considering that they only filled the ship's methane tanks to around 20% of its capacity for the long duration tests, this seemed to be more than enough. So adding the massive hot dog tank may be a sign of future changes to the static fire campaign. Whether that means performing more back-to-back tests or increasing the duration of the tests is something we will have to wait a few months to find out. And the reason for that is pretty simple. 1 year and 10 days after the inaugural static fire test of Ship 26 at Massey's, an apparent glitch in the matrix occurred as Ship 36 experienced a catastrophic anomaly on the pad. Between the humongous initial explosion and the subsequent fires which lasted for more than 16 hours, the damage was extensive. Since that day, it's been a 24/7 operation to repair, or in many cases completely replace, everything that was damaged or destroyed. There's no doubt about it, this was a huge setback. But looking on the bright side, SpaceX now has the chance to upgrade much of the infrastructure in ways that they likely would not have been able to otherwise without causing operational delays. So with that said, while I would like to go much deeper into each of these topics, it's probably best if I save that for a future episode once all of this work is complete. And if y'all want me to, I'll also go into some of the more technical details about how all of these systems within the tank farm actually work. After months of looking at thousands of images and analyzing all of these systems, I feel like I could probably give an official orientation for new hires at this point. But not everyone is interested in those types of details, so let me know in the comments. Until then, it's time for me to move on to a really fun topic that I've been waiting to cover for a long time. You may have noticed that I barely went into any detail about the flame trench and first of its kind water deluge system. I know many of you have been waiting for me to finish the version 2 launch mount series, but I can't do that without making comparisons to the Massey's flame trench, so I realized that I might as well give it an episode of its own. I was actually really close to finishing that before I stopped to make this episode, so I promise it will be out sooner than you expect. In the meantime, if you would like to support our channel, please consider becoming a monthly subscriber on Patreon. Your support goes a long way towards helping us continue to make this type of content. Before we go, I want to give a huge shout out to RGVAerialPhotography, Starship Gazer, LabPadre, and NASASpaceflight. Without their dedicated coverage of Starbase over the past 6 years, it would have been impossible to tell this story. I also want to thank our friends at Virtual Space 3D for preparing our new studio in the Megabay. Hopefully we will have a chance to get this place properly furnished soon. Alright everyone, I'll see y'all on the next deep dive investigation. For now, this is Stage Zero Zach, signing off.